Hi, I'm going to put a video solving this problem, which was requested by students. This was a problem from one of the review PowerPoint slides. Okay. So in this problem, we've got a bar that's supported by a wall on one side, which means there's some kind of force here at this end from the wall on the bar, and then by the other side, by a tension force in the wire. Okay. So the wall applies both a normal force and a friction force to the left end of the bar. So that means the normal force is going to be directed like this to the right. That's the normal force from the wall. And then the frictional force will be directed up to keep it from sliding down the wall. Okay. The ball weighs 400 newtons. We want to know what is the normal force applied to the wall on the bar. Okay. All right, so here we want to start by drawing all the forces on the bar, and I'm going to draw them again. Draw just the bar by itself so that we can go through all these forces more easily. Okay, so first we've got the weight of the bar. That's a gravitational force on the bar right here. Okay, going straight down. We've got the tension force here, and we've got the force of friction here and the normal force here. All right, so we want to figure out, and we've got our bar is 10 meters long, and that top angle is 20 degrees. I'm just going to draw this one here, which is 70 degrees instead. Okay. Erase this just to get a little less clutter. All right, so what are we going to do? We're going to apply that our net torque equals 0, and if we need to, we'll apply that our net force is also equal to 0, right? This is a static equilibrium problem, and a static equilibrium problem, we're going to find our net torque and our net force, set them both equal to 0, okay? So in a static equilibrium problem, remember, where you need to find the net torque, you can choose any point that you want to calculate your net torque around, right? And it's often easiest if you pick a point where there's a force that you don't know, because then you won't have to find the torque from that force, okay? So, but again, remember, you can pick any point that you want when it's static equilibrium. That no matter what point you pick, the torque net will always be 0, okay? But for our rotational axis for this one, I'm going to pick this point here, okay? And maybe that sounds a little bit funny to pick because that's where that normal force is that I want to apply. But the advantage of picking this point here is that now the torque from this frictional point is going to be 0 because the radius of that point is 0, okay? And we'll see in a second why that's going to help me, because that'll help me find the tension, and then that tension will allow me to find the normal force, because we can see that the normal force here and the tension force here are the only two things that have x components. So if I found the tension force, then it'll be pretty easy to find the normal force, okay? All right, so we're going to find, again, this is going to be our axis of rotation, and so then we want to find all the things that can cause a torque. I'm going to switch to this blue here, okay. So the torque from gravity is going to be force perpendicular times the radius, and that is a clockwise torque, which our convention says is negative. All right. And then the perpendicular force of gravity in this situation is just the weight, all right, which is 400 newtons. And then the radius here is the distance from this axis of rotation to that point, which is half of the length of the bar. So that's going to be that weight times 5 meters. So that's going to be 400 newtons times 5 meters, which is negative 2,000 Newton meters. Okay. Now we also want to find the torque from our tension. So the torque from our tension is going to be F perpendicular R tension. Okay. Now this one is going to be counterclockwise, so it's positive. All right, so let's find the perpendicular to that radius component of our tension. So pick a different color so we are less clear on top of each other. So I'm going to use this pink for the tension force. So this is our radius for our tension force, and then the perpendicular component, perpendicular to that radius, is going to be this pink component that I just drew. Okay, if we draw our tension force like this, we could also draw it as this side here. This is the perpendicular component. All right. So if we have that original 20-degree angle up at the top, then that F perpendicular then is T cos 20 degrees, because that's the adjacent side. Okay. And then, oops, sorry, I switched back to the wrong color. Let's pick back this blue. All right. So then the torque from that wire is the tension on the wire times cosine 20 degrees times the length of the whole bar, which is 10 meters, okay? And we know that these two tensions, these two torques here and here add up to 0, all right? So we've got our first one is negative 2,000 Newton meters plus T times 10 meters times cosine 20 degrees equals 0, which means that T is going to be 2,000 Newton meters over 10 meters cos 20 degrees. All right, so I'm going to plug in numbers for this. And we find that that tension is 212 Newton meters. Okay. Now let's go back up to our free body diagram here. We want to know this normal force. Okay. This normal force needs to be equal and opposite to the X component of this tension force, right? Because those are the only two forces in the X direction, okay? So again, if I've got my tension force like this, got this 20-degree angle here, this is the tension force parallel to the bar. That parallel is going to be T times sine of 20 degrees. And that's going to be equal in magnitude, but opposite in direction to that normal force. Okay. So that is 212 Newton meters times sine of 20 degrees. Which gives us 73 Newton meters. Okay, which again is one of our answers. Okay. All right, and again, if you wanted to solve this by picking a different point around which your bar is rotated, that's okay, but I think the one that I've chosen here is the easiest one for simplifying the algebra, and it kept us from having to use our net force equation, which we would have had to do if we had rotated it, for example, around its center. All right, that's the end of that video. I'm going to scroll back down to this bottom part just in case you need to see the last of that work a little bit more.